Welcome class to lesson 9.2. In this video, we're going to go over the mastery worksheets on exponential functions. In the previous video, we were introduced to geometric sequences, and now we're just evolving to the next step, which is regular exponential functions. Now, the graphs would look similar when you're plotting points, but whereas geometric sequences were often dots growing or decaying, getting smaller, we will now be graphing more lines. Now, exponential functions follow this general format, y equals a times b raised to the x. Let me give you an example here. It could be y equals perhaps 2 times 3 raised to the x. And the graph would look something like this. An exponential growth would look, well, the way what I just drew here was actually called an exponential growth. As you can see over time, we look at the graph from left to right, and the graph is growing exponentially. It's growing very quickly, similar to a geometric sequence. Now, graphs can also be going the opposite direction, which is decay. Still following the same format. It might be better if I handwrite it right here. Y equals 2 again, but instead of 3, maybe I'll make it like a 1/3. A value between 0 and 1. And this would qualify as a decay graph. If I were to graph it, it would look something like this. And we'll be graphing shortly on Desmos, just so you can get some better graphs here. Now, graphs can also be reflected across this x-axis. We can also have graphs where they'll be reflected, and it could be like a mirror image. Now, these kind of graphs would have the same kind of equation, except the main difference is there would be a minus sign in front, because that minus sign in front tells us it is reflected across the x-axis. Reflected across. Now let's look at Desmos. Let's draw our basic exponential graph first. Y equals 2 times, let's see, I'll change the number. I'll just do 2 here, and I'll raise it to the x. Here's our basic exponential graph. And let's do a decay graph. Y equals 2 times. And this time I'll make it a little fraction here. And we're going to raise this one. I might have to put this in a parentheses so the computer will understand what we're doing. And I'll raise it to the x. As you see, the blue line, it's going to have a decay here. It's actually getting smaller over time, while the exponential growth equation is getting bigger. They both have the same y-intercept of 2. So if we plug in 0 for x, anything raised to 0 is 1, and 2 times 1 is 2. So we will get 0, 2. Now let's look at these same graphs, and we're just going to reflect it by putting a minus sign in front. Put a minus 2 times 2 to the x. And here's a decay graph. See the graph in green. It's just a reflected line. It looks almost the same as the line in red here, but it's reflected across the x-axis. And we have another type of graph here. Y equals minus 2 times, and we'll do the 1/2. 1/2 raised to the x. And this is just a reflection of the blue line across the x-axis. So we actually made a nice little pattern there. Now let's look at the worksheets. On the mastery worksheets, it's just giving us a little bit of, it's kind of the same information we just went over. They're showing a growth equation. It might be a little hard to read, so I'm going to write what it says there. It's y equals 5 times 2 to the x. Remember, this would be the a value, and this would be the b value, a, b to the x. And that's a growth graph. If we look at the second graph, there's a minus sign in front. So normally it would have been a growth equation, but now instead with the minus sign, it's reflected across the x-axis. And this equation is minus 3 times 4 to the x. Again, the a here this time is negative 3, and the b is 4. On the third example, we have a decay graph. See, the line gets smaller. And the equation here says y equals 2 times 0.6 raised to the x. So there's the a value and the b value. It gives us some information at the top of the page. You can also look up here. See, a here was positive, and here b is a fraction between 0 and 1. That's what 0.6 is. That's a decay. Last example, a is less than 0, which means it's negative, and b is in between. Again, normally this would qualify as a decay graph, but the negative sign, of course, means it's reflected. So the numbers, when we look at it, is actually getting bigger. Because it's reflected, it's reversed. A decay is kind of like a growth, because the numbers are actually getting bigger. Even though all the numbers are negative, they're less negative over time. And this equation is y equals minus 2 times 4/5 raised to the x. Here's the b value, and here's the a value. And the b value, again, is between 0 and 1. This negative sign is what reflected across this x-axis. And here's the table of values where we just actually plugged in some values. They gave us an x points to plug in of minus 1, 0, 1, and 2. They gave us the equation. And we got the y values by plugging in. Minus 3 times 2 to the minus 1. You can always enter this into a calculator, but I want you to understand when you have something raised to the negative 1 power up here, we just reflect it. Or I just we just kind of take the reciprocal. So minus 3 times 2 to the minus 1 is the same thing as minus 3 times 1 over 2, which of course is negative 3/2, which gave us the value here of negative 1.5. And here when we graphed it, this would have been a growth equation, normally looking something like that. But because the negative sign in front, it is reflected. And that's why this graph is going down. Now let's look at the homework. Okay, number 6. It says graph each exponential function. So now we're going to be plugging in the values here. All right. Now let's look at number 6. Here we'll be plugging in the values of minus 2, minus 1, 0, and 1. So in the first case, we have minus 4 times 0.5. I'm going to write that as 1/2 to the minus 2. You could type this in the calculator and get the exact value. Excuse me. Or you could do this by hand. Minus 4 times 1/2. When it's raised to a negative exponent, we just flip it. So it's times 2 squared, which of course is 4. 4 times minus 4 is minus 16. The next value is minus 4 times 1/2 raised to the minus 1. 1/2 raised to the minus 1, so we flip it to just 2 over 1. So this one would be minus 4 times 2 over 1 raised to the 1, which is simply minus 8. The next one is minus 4 times 1/2 raised to the 0. Now this is important to remember. Anything raised to the 0 is 1. So 1 times minus 4 is minus 4. Lastly, minus 4 times 1/2 to the 1 is simply minus 2. Now if we were to plot this, we have minus 2 minus 16, minus 1 minus 8, 0 minus 4, and 1 minus 2. And there's our graph. That negative sign told us we were going to be below the x-axis. So if you remember this, it kind of just gives you a little hint that where we should be getting our points at. And this is normally a decay graph, but because it's upside down, with the negative sign, decay becomes like a growth. Here, now let's look at number 7. Y equals 2 times 5 raised to the x. Now in this problem, the a value of 2 is positive, and the b value of 5 is greater than 1. So this graph should be a growth equation. It should look something like this when we're done with it. That would be a growth equation. Let's see if we're correct. 2 times 5 raised to the minus 1. We could type that in our calculator, or we could simply do it by hand. 5 raised to the minus 1 is just 1 over 5 to the 1, which of course is 2/5. So the value is 2/5, or we could write it as a decimal, 0.4. Now, 2 times 5 to the 0. Anything raised to 0 is 1, so it's 2 times 1, which is 2. Then it's 2 times 5 to the 1, which is simply 2 times 5, which is 10. And 2 times 5 squared, which is 25. 2 times 25 is 50. See, so minus 1, 0.4. It's really small, close to 0. And then we have a point at 0.2, which is a little bit higher. And then 110 and 250. So here's our equation here. It's growing very quickly. And this line, of course, will be getting very small going to the left. Number 8. Now this negative sign tells us it's going to be reflected across the x-axis. Minus 1 times 2 to the minus 1. This, of course, means the 2 is going to be on the bottom. So minus 1 times 1 over 2 to the 1, which is minus 1/2. And then minus 1 times 2 to the 0, which is simply minus 1. And then minus 1 times 2 to the 1, which is minus 2. Lastly, minus 1 times 2 squared, which is 4. Minus 1 times 4 is minus 4. Now let's plot these points. Minus 1 minus 1/2. It's about right there. 0 minus 1. And then 1 negative 2. And 2 negative 4. And of course, this line just keeps approaching the x-axis on the left, and it's getting more negative as we go to the right. Now in this video, I started off with the what I would think is the more difficult problems. I actually want to go back to the earlier problems now. It's just a little slightly different idea here. Sometimes we'll have a table of values and we have to decide whether these points actually form an exponential function. We were able to before to tell whether equations were linear functions by looking for a constant rate of change. But for exponential functions, we're not looking for a constant rate of change. We're looking for like a more of a multiplier of change. For example, this first example of 3, 4, 5, 12, 7, 36, and 9, 108, each time we are multiplying by the number 3. 12 to 36, we multiply by 3, and times here by 3. It's the same number. And because we're multiplying by the same number, and it could be a fraction. It could have been 1/3 or 1/2. But because it's the same number we're multiplying by, it is an exponential function. If we were to graph this, this is actually a growth function. On the next example, let's see, to go from 2 to 4, multiplying by 2, but the next one, we're not multiplying by 2. We're not multiplying. We'd actually be multiplying by 3 over 2 or 1.5. And the next one, we'd actually be multiplying by 4/3 to get to 8. So it's changing each time. So it's not exponential. But this graph is not exponential. But if we notice, each time we're adding 2. This is a first order difference, which means these points form a linear equation. They actually form a straight line, a linear, because the same points, we're either adding or subtracting the same value, and that's a first order difference. But in this video, we're just identifying whether points are exponential functions or not. So this one is not. Now here, I guess we're actually using the word a constant ratio. Ratio meaning we're multiplying. It can also mean dividing, but division is just multiplying by a fraction. That's what division is. And we have an example here. Population of a school can be described as by the function f of x equals 1,500 times 1.02. Now this is the starting number. There must have been 1,500 students in the school at the beginning. And it's growing because it's greater than 1. See this 0.02 here? Greater than 1 means it is growing, and it's actually growing at 2% a year. That's what the 0.02 means. So it's growing at 2% a year. And what is the population in 12 years? Here we're just plugging in the x value of 12, and we enter that in a calculator. They got about 1,902. These are people, so we can't have decimals. Now let's look at the homework. Number 1. Now for these problems, the rate of change on the x's are going to be okay. It's going to be the same rate of change. So we don't have to worry about the x's. Because if these rates of change actually vary, we have to adjust these numbers here to see if it is still a constant ratio. That would be more difficult, and it's nothing in this homework assignment that'll be that tricky. For the first example, we are going from 1.5 to 3, 3 to 6, and 6 to 12. Is there a constant ratio? Are we multiplying by some number each time? And we are. We are multiplying by 2. So this is an exponential function. Number 2. Here we're multiplying by 2, multiplying by 3, and then we're multiplying by 4. These numbers are not the same. So this is not an exponential function. So I'll just write no. Number 3. Minus 2 to minus 10. Minus 10 to minus 50, and minus 50 to minus 250. Each time we are multiplying by a constant ratio of 5. So this is an exponential function. So we'll just write yes. Now let's look at our first word problem. If a rubber ball is dropped from a height of 10 feet, the function f of x equals 20 times 0.6 raised to the x gives the height in feet of each bounce, where x is the bounce number. What will be the height after the 5th bounce? So for this problem, we just have to plug in x equals 5. The ball is dropped from a height of 10 feet. See, this number here where it says 20 should have been 10, because whenever you drop a ball, when we drop a ball and it falls to the ground, the highest it can ever bounce is its original height. That is the maximum height any ball can bounce up to if you're just dropping it. Because this ball, when it drops, it has a certain amount of energy, certain amount of potential energy. And the truth is, there's actually energy loss or work done by friction. And the ball's only going to bounce so high. And then it's going to bounce so high again. It's a percentage each time. It's going to keep getting smaller. The only way a ball can bounce higher when it's dropped is if the ball has both potential and the other form of energy, kinetic energy. If we're throwing the ball down. So the ball's going down really fast. Okay. I apologize that the screen flickered there. I had to reboot my computer for a second. Now, back to this problem. If the ball is actually thrown down, so it has both kinetic and potential energy, the ball can actually bounce higher than the height that the ball was started at. But that's the only way, if the ball is actually thrown down. Otherwise, the graph up here is going to be it. And most times when we do these dropping ball problems, you'll see these a lot, especially in your science classes, like a physics class. It's the starting height times this this function, like the 0.6. This means it's falling each time. It reaches only 60% of its previous height each time. That's what the 0.6 means. But here it went up higher. So on the first bounce, 20 times 0.6 is 14 feet. It actually went a whopping 14 feet on the first bounce, which is amazing. If you just dropped the ball and it went up to 14 feet, you would violate the conservation of energy and also the conservation of momentum. And if you could violate those two laws, you would be the wealthiest person on earth because you could create energy from nothing. So there are people who are actually trying to do that in physics, but it hasn't happened yet. So let's get back to the problem. In this problem, what would the height be? It would be 20 times 0.6 raised to the fifth. And we can enter this in our calculator. Let's get it here in our calculator. Well, let me move the calculator over. Here we go. Okay, and let me move it up. It'd be 20 times, parentheses, 0.6 raised, which is like a caret key, to the fifth. And we get 1.55. It says rounded to the nearest tenth. So we'll say 1.6 feet on the fifth bounce. And of course, it'll be 60% of that on the next bounce. And 60%, and keep going until it stops bouncing. Now let's look at the last word problem, number 5. A population of pigs is expected to increase at a rate of 4%. It's increasing, so it has to be greater than 1 because it's increasing, and it's actually 1.04. That is the 4% increase. If the original population is 1,000, here's the starting population here of 1,000. Much like the last problem, instead of 20, the starting number here should have been 10. Now, what will the population be in 12 years? So we're just going to enter 12 here. So we're going to do 1,000 times 1.04 raised to the 12. Let me clear it here. So we're going to do a starting population of 1,000 times 1.04 raised to the 12th. And we get that many people. Now, keep in mind, these are human beings, so we can't have 0.03 of a person. So we're going to have 1,601 persons at this time. 1,601 persons. It's a word problem, so we should always have units. Well, that concludes this lesson.